now that we're recording. We want to make sure that we hit all the highlights. We've got a list of topics on the syllabus in the course content. And there are some things that we want to ask about each of those topics. There are it's a list of 18 things sitting on the front of the syllabus. So we want to know, can we identify when we did this, like what chapter we were doing this in, when, beginning, middle, or end of the semester, when we're talking about derivatives, when we're talking about integration, just generally where things happened. And what kind of problems are we faced with? Were we faced with? And where do those problems fit into the things that we've studied previously and the things that we're probably going to be studying in the future? And also, what kind of conversation can we have with, say, an instructor, with our fellow students, or with future students, people that we might be helping out? Like if we happen to be studying in STEM Center, what do each of these topics bring to that conversation that you're having with future students that you might be helping out in the STEM Center as you carry on the oral tradition of learning math? All right, let's grab an example from our syllabus. All right, so the first three are all about vectors. So we see those first three kind of grouped together. So we've got vectors and vector operations in dimensions, vector and parametric equations of lines and planes, rectangular equation of a plane, dot, cross, triple products, and projections. So this is how you can tell when something is written by a committee and they're not reading each other's work. This is definitely a draft of something that someone's like, oh, hey, let's all go to lunch. So I'm pretty sure that these three entered in. They showed up like right at like 11:45. Like, oh, dude, let's put these first. And like, oh, all right, now should we phrase this a little bit better, be a little more succinct? And like, oh, dude, it's 11:45. And I want to make sure we're at the front of the lunch line. It's like, oh, right, send it. Then after lunch, they were all sleepy. It's like, oh man, are we going to revise that? It's like, oh, no, let's just put some more stuff on there. We'll put it first and we'll sort it out later. Then someone hit publish and then we looked at it and we're like, oh, well, there it is. I mean, vector operations in dimensions and a whole separate thing, dot, cross, and triple products. It's like, oh, those are vector operations. What? Yeah. It's all beside the point. I'm not making fun of you if you're on this committee that put this list together. Okay, that's not true. I'm totally making fun of you, but I would have done the same thing, especially if it happened right before lunch. A lunch that you know they would be serving, because I'll only go if luncheon is provided. Then I'll complain about the lunch, but that's just because I'm a dick. So we've got these three things. We got vectors, vector operations. And that kind of says a lot. Number two is a more specific thing, because number two is about equations of lines and planes. There's like the rectangular equation of plane, that's in equations of lines and planes. But equations of lines and planes, vector and rectangular, and then dot, cross, triple products, and progressions. So when did we talk about these things? This was kind of an easy one. I'm glad that we led with this one. This one started off in, for this particular book, this chapter was 13. This was chapter 13. This was vectors. So when did we cover this? Chapter 13, vectors. When did this happen in the context of this class? This happened early on because it was very important in describing things in 3 dimensions. And the vectors were very useful and very important in describing things in 2 and 3 dimensions. It's a big hobby of ours in this class and helps us frame all the topics in the class. So this is foundation. This is an important tool for multivariate topics. And I think this book literally calls chapter 13 vectors an important tool for calculus. Some of you have been through a linear algebra class, and you're like, oh, linear algebra was a lot about vectors as well. The stuff that you learn in linear algebra about vectors is the same stuff that you learn in Calc 3 about vectors. It's the same stuff that you learn in Physics 250 about vectors. Physics 250 is F, right? 260 is EF, 270 is like all the rest of it. Yeah. But they kind of show up and it looks a little bit differently. It'll look different from different class to different class as we bend this concept to our purposes. So as far as other categories, other places we'll see this, we see these things. In the C also category. There are also probably an engineering class called engineering statics. This establishes a foundational tool. What kind of things? And these are we have to learn about the operations, vectors and vector operations. And then specifically, we've got this extra bullet point for dot product, cross product, and triple product. So this raises the question, what kind of problems did we have to do with this? Do with these problems? And you can remember things like finding dot products, finding cross products. And there are details that we might or might not remember, like how to find the cross product of a couple of vectors. If in some incredibly archaic fashion, I just hand you 2 vectors and say, find me the cross product. And you'd be like, oh, you mean that determinate thing? I'm like, oh, yeah, do that. Well, I'm going to mess up a sign somewhere. I'm like, oh, and that's the reason that you'll never be an engineer. School is weird sometimes. School is weird sometimes. Well, what kinds of things do we know about dot product? What kind of things do we know about cross product? What is our short description of what's a dot product? How would we describe dot product? So when you come home and someone says, and you're in your, whoever's there at the house living with you, hey, what do you do in school? Oh, we use dot product. You're like, oh, what's dot product? As if anybody asks you about your schoolwork. I don't know. Maybe this is just some archaic thought when a kid comes home from school and they say, what did you learn in school today? And then the kid says whatever it was, and then the parent calls the school to complain. I don't know, maybe that's a modern thing. So what is our short description of dot, cross, and triple products? This got separated from vector operations. They're just operations that we perform on vectors, like addition and scalar multiplication, but they get their own thing. How would we describe dot products? Scalar and vector multiplication. So what is dot product? What is cross product? So just grabbing that third one, dot product, cross product, triple product. What is the dot product? We know that the dot product is the scalar product, so that's good. That's the scalar. And we know cross product is the vector product. We know those super short descriptions, but that's not very descriptive of what they're telling you. So we need to think about how we describe dot product. We think about what the cross product tells you. Think about how do we compute these things? And what does that tell us? How do we compute the dot product? What does that computation tell us? How do we compute the cross product? What does that computation give us? What does that tell us? I'm fairly confident that if we had an in-class final exam, and I gave you two vectors to find the dot product of these vectors, and then I gave you some other information to find the dot product of these vectors, and then find the projection of one vector onto the other vector, or say that in a different fashion, decompose these vectors into a component in the direction of this vector and a vector perpendicular to that vector. But that brings us back to why we would be doing this. I'm really confident that if I just hand you a couple of vectors, you all can tell me what the dot product is, and you all can tell me what the cross product is. Even if it's like a timed test, I hand you two vectors in R3 and say, find the cross product. And you'd be like, oh, by hand? I'm like, oh, hell yeah. And you'd be like, oh, but why though? And I want to see, the answer would be like, I want to see who can keep track of the negatives. How much detail can you maintain? How much focus can you maintain in a 2.5 hour test so that you don't drop a negative and lose points because you miscalculated, because you did a minus J, but then forgot to switch those two terms around. I am fairly confident that if I said that there's going to be a timed quiz or test or final exam, and you'll have like 10 minutes to compute a cross product by hand, that y'all would be like, oh, all right, bet. And I would just practice it. Like, well, I know that I am shitty about this, and I'm going to drop a sign somewhere, so I'm going to practice it. And some of you are like, oh, I know that I'm really awesome at this, and I have really good focus, and I keep track of lots of numbers. And y'all be like calculating cross products in your head, and that's fine too. And you would do that. So prosecution stipulates that if I told you you had to calculate cross product, you would sufficiently prepare. Except some of you would walk in on the final exam and they're like, oh, wait, what's going on? They're like, what's the final exam today? And I go, oh, that's great. Who are you? I go, I'm the instructor for the class. Oh, okay. Can I have a copy of the final exam? So I made a whole ass copy, and I know you're going to leave most of the blank. Why don't you just tell me your name and I'll write it down? I'm just kidding. That's the conversation that happens when a student walks into a class and they go like this. They make that face that says, oh, is there a test today? It's especially fun if you have a student that only comes in periodically, fairly reliably, like on Thursday. That's when I want everybody to bring out a packet of paper, and especially if that's coming late. Everybody brings a packet of paper. Like today, when Bob walks in, we're gonna make it look like we're getting tests. I'll be like sitting down at the desk, off, you know, do like writing stuff down. Then they'll walk in, and be like, "Oh, I thought all the tests." Like, "Oh, here you go, have a seat." And then they'll like have the paper, possibly a cover page, like that, 253, confidence 3. Right there. Good term. Good term is that. That's a big, oh shit, they come on paper? I haven't seen any. Then they sit down and fold over problem 1. April 2. Anyway, what are we talking about? So, for each of the items on the list, this is the conversation that you need to have with yourself. Do I know where this came from? Do I need more information on what's going on here? What kind of problems did you face? What do the problems look like? Just what are the mechanics of the situation? What are a few of the applications of the situation? How do we compute the thing? What does this computation do? Where have I seen this before? Where am I going to see this in the future? In the case of vectors, it's going to be a linear algebra and differential equations, or do you have a lot more crossover? So, how many of you have had linear algebra already? Are you in it right now? Anybody planning on taking it over the summer? Linear algebra is a good summer class because linear algebra is kind of like one of your easiest math classes. I mean, because you've been through calculus. Like if you handed linear algebra class to like people that were still in algebra, they'd be like, "Oh no, this is unacceptable." But once you've been through calculus, you've seen some shit. You're a little bit more of a hardened math student. You know, like on linear algebra, we'll talk. So it's a good one to kind of like knock out things. So for each of our topics, each of our items, you'll also notice another thing that I did. I grouped these first 3 together. Instead of just looking at each individual piece, I just grab those first 3. And these first 3 are all related. That's the kind of familiarity we want to build with each of these topics. Then we want to figure out what kind of questions might show up. Is there going to be a question on a final exam that says just compute this cross product, or am I going to have to compute a cross product in some kind of context? I'm going to have to know what this cross product is for. I don't know if it's the demonstration of finding the cross product that's important, or is it important to know what the cross product is about? Just really quickly, what is the cross product tell you? Remember, the cross product is going to tell you a vector that is perpendicular to the two vectors in the product. U cross V is a vector perpendicular to U and perpendicular to V. Then we want to think about, why did we care about that? I only said it like a few hundred times. Why do we care about a vector perpendicular to these two vectors? Because 2 vectors make a plane, and this one vector, in R3, that leaves 1 more dimension, and this one normal vector, one vector to describe an entire plane. We can use one vector to describe a direction, and now in R3 at least, we can use one vector to describe a plane. And then we start thinking, did we do cross product in R4? And I'm saying we did not. Cross product is an R3 thing. Dot product is an R anywhere thing. Cross product is kind of specifically an R3 thing. Then we think about where else that happens. Where else the cross product when did cross product most recently show up? If we take a look at the bottom down here, when did cross product most recently show up? And we see down here, that's Stokes' theorem, right? That's theorem Stokes. Stokes theorem. I was looking at it from a distance. We have Stokes theorem. Stokes theorem said the integral of the curl of a vector field dot dA is the line integral around the boundary of the region. And curl was a cross product, told us how swirly the vector field is. So interrogate yourself on each of these 18 topics, each of these 18 items. Some of them get crammed together. Like when we talk about Green's theorem, Stokes theorem, and the divergence theorem, that's all related to divergence and curl. 17 and 18 clearly go together. All right. That's going to do it for today. That's what we're going to be talking about for the rest of the semester. Everybody have a good day, and I'll see you all tomorrow. See you Thursday.